Yesterday we stopped here, and yeah, actually here. So we finished the part about taking the derivative of the electric potential will give you the electric field, or at least the component in that direction. And actually taking the gradient, you're able to get the electric field in an other direction. So now we talk about another similar concept called the electric potential energy. So actually, we now see that we have two charged particles, Q1 and Q2. So you can understand that if we have two positive charge or maybe negative charge, if we have two charged particles placed together, then there will be a force repelling them or attracting them. For this case, if both are positive, they should repelling each other. They should repel each other. And in this case, if we really need to put a Q2 from infinitely far away to this point, then we need to do some work or need to spend some energy to do so. And actually, for this system itself, it will store some energy there. And this energy is calculated by this equation. Actually, it's just to integrate the F over the, integrating it. And then you get the potential difference. And then this is actually what the energy stored here. So if you have multiple particles, here, then you need to calculate the energy stored 2 by 2. So for this summation, usually the summation sign is like summation for I from 1 to n, then you will count n terms there. But here, within this summation, you have I and j to be the dummy variable. And actually, it only tells you that I is not equal to j. If we don't really have this constraint, if we don't really have this constraint like I from 1 to n, j from 1 to n, then we'll have n squared terms. But actually, we'll not count Q1, Q2, and Q2, Q1 for 2 times. So, and also we'll not count something like Q1, Q1. So in this case, there are only NC2 terms. It's just like if we have I and j to be maybe 1, 2, and 3, and then 1, 2, and 3. So we only count this one, and this one. 1, 2, 1, 3, and 2, 3. So this is actually NC2 terms. NC2, or some books will write it as N2, which is n minus 1 over 2. So we have quite a lot of terms there if n becomes large. For example, if we have three particles, we have three terms. If we have 4 particles, then we'll have 6 terms. Is it okay? Is it okay for this summation sign? Usually, I will not ask you to find the total energy for maybe 5 particles. There will be 10 terms. So we have a sample problem. So here, 3-point charge Q1, Q2, and Q3 held in fixed position by forces that are not shown. So what is the electric potential energy U of this system? So assume that D equals 12 centimeters. Q1 equals plus Q, minus 4Q plus 2Q. Q is 150 nanocoulomb. So the total U is U12 plus U23 plus U13 or U31. So we have this vector K and then summation Qi Qj over Rij. So so we have K Q1 Q2 over D plus Q2 Q3 over D plus Q3 Q1 over D. So it is nothing but K over D Q1 Q2 plus Q2 Q3 plus Q3 Q1. So we substitute all the number. K is 8.99 times 10 to 9. D is 12 centimeters, 0.12. So Q1 is 1 times times 150 nano, which is this one, and then square, because we have Q1, Q2, Q2, Q3. So this Q will appear 2 times for each term. So we have squared there. So we have 1 times minus 4 plus Q2, Q3, minus 4 times 2 plus 2 times 1. 2 times 1. So the answer will be minus 1.7 times 10 to minus 2 joule. Any questions? No questions. Okay, so next we have another sample problem. So suppose we have an alpha particle. Alpha particle is 2 proton, 2 neutrons. 2 proton, 2 neutrons. So move into a stationary gold atom. So there are 79 protons and 118 neutrons. So passing through the electron region that surround the gold nucleus like a shell and headed directly toward the nucleus. So the alpha particle shows until it momentarily drops when it's centered at radius r equals from the nucleus center. So R. So simply speaking, it means that the alpha particle is coming from this alpha particle, coming from far away, and then it goes to the right side, and you may imagine you hit the gold nucleus, assuming that it is at rest there. So if you can imagine you have 2 balls. One ball is stationary here, and then you have another ball hitting it. So these 2 balls will collide with each other, and then maybe they will separate again, or maybe whatever, depending on what type of collision. However, because these are alpha particle, which means it has 2 positive charge, 2 plus 2e, and then in the gold atom there are 79 protons, so it has plus 79e, so that they will not touch each other because there will be Coulomb's force to repel them. So as long as this particle going from far away and then approaching the gold nucleus, then the alpha particle will decrease, will decelerate until it stops and then go back. It will not physically touch each other. It will not physically touch each other. So this is the electromagnetic force. So it asks you what was the kinetic energy of the alpha particle when it was initially far away? It tells you that up to R equals 9.23 femtometer, then the alpha particle stop and then turning back. So what was the initial kinetic energy? And then assuming only the force acting between the alpha particle and the nuclear force is the electrostatic or the Coulomb's force. So we can assuming that there are conservation of mechanical energy. So we have Ki plus Ui, the initial mechanical energy equals the final mechanical energy, Kf plus Uf. So Ki is what we want to find, and actually Ui should be 0 because we are assuming that it's come from infinitely far away. So Ui should be 0. And then Kf should be 0 because it stopped at this point, which means that there are no velocity. Velocity equals 0, which means the kinetic energy should be 0. So this term should be 0. So Uf is what we can calculate. So actually we have a Ki equals Uf, which is K times Q1, Q2 over R. So K is 8.99 times 10 to the 9th power, and then Q1 is 2 proton, and then the gold atom is 79 proton, and then times 1.6 times 10 to minus 19 quantity square, and then the R is 9.23 times 10 to minus 15. Femtometer is 10 to minus 15 meter. So actually it is 3.94 times 10 to minus 12 joule. So this could be a form of the answer because we use the joule as the SI unit. But in solid state physics or modern physics, another unit is also very popular is the EV. So how to convert joule to EV is to divide this number by 1.6 times 10 to minus 19, which is the elementary charge. So after dividing it, this number is 24.6 mega EV. So actually the EV means you use 1 volt electric potential to accelerate an electron, then the energy will be 1 EV. So both are acceptable. So joule is of course acceptable, and then mega EV because this unit is quite small. So when you come up with joule, then you will have the number like a 10 to minus 10, 10 to minus 12 or whatever. So using the EV, it will make this number larger. So any questions? Okay, so next, here we talk about the potential of a charge isolated conductor. So here, on the right side, this is a car, and then, so this is a lightning hitting the car. And actually, this guy is safe. This guy is safe because actually the car is a conductor, which means that the whole car shares the same energy, which means that as long as this guy need to be threatened by the lightning, which means that suppose the guy is standing there, then suppose there is a lightning hitting it, then there will be large current going through it, then of course this guy will die. And for this case, suppose this guy is in a car, so this guy is here. So actually the car itself is conductor, so that the car itself share the same electric potential, which means that there will be no current going through the guy, as long as the electricity need to make fatal damage to people. It need to have not only high voltage but also high current, which means that power should be large enough to make things make it fatal. As long as this case the car share the same voltage, then the current may go through this way to the ground, so there will be no large current going through the guy. And in this case, it means that we can actually use this equation to demonstrate this idea. Is suppose we have a plot V of R like this. Within 0 to 1 meter, the voltage is maybe 9. This is 9 kilovolt, and then exponentially decay. So we know that this is V, so that we take the derivative of this curve, then we will have the electric field. So this is proportional to 1 over R. 1 over R. Yeah, 1 over R. So if you take the derivative, it would become 1 over R squared. Of course, we have a minus sign, but we also have a minus sign here, so it cancels. So it's proportional to 1 over R squared. And for this part, it is a constant, which means that taking the derivative, it will be 0 here. It will be 0 here, or the rise, or in the other direction, you can integrate this part. But of course, there will be some initial voltage or initial potential there, and then you integrate this part is 0, so that this part doesn't change, and then you integrate this part, but with a negative direction, so that it will try to decrease gradually. So this is how we can make use of this one. So actually, electric potential is very useful as long as we don't really need to consider the electric field at the first moment. We can calculate the electric potential easier than calculating the E field directly. And then after getting the electric potential, which is a scalar field, and then we take the gradient or the derivative, and then we can get the E field. You can get the E field. So up till now, we have learned also E, V, and U, and also the F, which is in chapter 21, chapter 22, chapter 23, and chapter 24. Actually, this is also in chapter 24. So we have, in the electrostatics, we come up with 4 most important variables. So actually, they can be linked like this. So we have the electrostatic force in chapter 21, and this is linked by F equals Q0E, so that we can get the electric field in chapter 22. So by taking the gradient operation, and then of course with a minus sign, we can get the electric potential. Or in the other direction, we can use the line integral to obtain the electric potential first, and then we can go back to get the electric field. And the electric potential and the potential energy also related by this linear relationship. So U equals Q0V. Here we have a F equals Q0E. So that it will be like this. So this is the potential energy. And even in mechanics, even in classical mechanics, you will also know that the potential energy is negative F dot ds, which is the minus work done. So this is the work done, F dot ds, and then integration is the work done. So this is actually a line integral. If the path is not a straight line, then you need to seek for a line integral. So similarly, if you go from here to here, you use the line integral. So here is F, U. Here is E and V. So if you go from the electrostatic force to here, then which means that you have gradient U. You have gradient U F. Minus gradient U is the F. So they share similar structure of the mathematical equations. So here we have some additional example. Yeah. So here, yeah. So actually, a thin plastic rod L, capital L is 13.5 centimeter, and uniform charge 43.6 femtocoulomb. So in terms of D, find an expression for the electric potential at P1. So here we write it as a dV equals K times dQ over, so suppose this one is X, this one is X, and then this is the dx, or within it, this is the dq. So dq, and then, so this distance is d plus x. So we similarly, assuming the linear charge density is lambda, so lambda dx, dq is lambda dx, so that we have k times lambda dx over d plus x. So this d and this d are different. This d, the bottom one is this one. The bottom one, maybe I should, yeah. The bottom one, the bottom d is this one. Okay, so when we need to calculate the total potential, so V equals integration of dV, and then we can substitute this term into here. So we have k lambda x dx over d plus x. Actually, we need to integrate from 0 to capital L, 0 to capital L. So d plus x is actually the same because d is a constant to the x. So we can have k lambda, and then this integration is the log d plus x, and then evaluate at L and 0. So it is nothing but k lambda natural log of d plus L over d. d plus L over d. So this is a general expression, and then we can evaluate, substitute all the numbers into it. So we have k equals 8.99 times 10 to the 9th, and then let me see, L lambda. Okay, and then lambda L should be the total Q, which means that lambda should be Q over L. Q over L. So Q is 43.6 times 10 to minus 15 Coulomb, and then L is 0.135, and then natural log so we can have like 1 plus 0.135 over d. So slightly simplify it, we can have a 2.9 times 10 to minus 3 volt, and then log 1 plus 0.135 meter over d. So within the lateral log, there shouldn't be any unit, any dimension. So we only have dimension for these parts. Any questions? Okay. So next, substitute the variable x for d, which means that we just simply copy this one. Right? Not this. Yeah, okay. So we have v. So it asks you to substitute variable x instead of d. Which means that it's just fixed. Yeah. I mean, this d is called x now. But actually now the x-axis is in this direction because we count this way is a positive number. It's a positive number. So v of x or maybe we can write it as a v0 ln 1 plus L over x for simplicity, because You need to write a lot for V0. Just V0 is that one. And L is of course 0.135 meter. So now it asks you find the expression for the magnitude of the component EX of the electric field at P1. So we can simply find it by taking the derivative. EX equals minus dV of x dx. Taking the derivative with respect to x and then take the minus sign. So it will be minus V0 and then log, take the derivative, will be 1 over 1 plus L over x, and then chain rule, we need to take the derivative with for the argument. So the derivative of 1 is 0, and then we have minus L over x squared for L over x, So it turns out to be V0 here, L, and then we distribute this x squared into here, or distribute 1, so we have x times L plus x. Okay, so so it will look like this. So we can substitute the number. Substitute the number here, so that we have V0 is 2.9 times 10 to minus 3 times L is 0.135, and then 0.135 plus x times x. So this is the expression for E sub x. So next, what is the direction of the E relative to the positive direction of the x-axis? So actually, you can simply imagine that for part C, it should point to the left side. Or for the original axis, x-axis, original x-axis should be this way. But maybe this question is not written really well. But actually, left side, we do not misunderstand this, because this is a positive charge. So at this point to the left, the E field should point to the left side. Because it's originally just asks you to substitute x for d. So in that case, for this expression, it considers the x-axis to be point to the left side, but it again asks you relative to the positive x direction. But actually, for this x direction, it is that way. So it makes the whole expression to be really strange. It should be like minus x rather than minus x. But it doesn't really matter. Oh, this is good enough. So any questions? So next, what is the value e sub x at d equals 6.2 centimeter? So we only need to substitute the number. So we have V0 L L plus X times X. So we substitute the number 2.9 times 10 to minus 3 times 0.135, and then 0.135 plus 0.062 times 0.062. So it will be 0.0321 nano per coulomb. And for the symmetry, EY, what is EY at P1? And of course, EY should be 0. EY should be 0. D. EY should be 0 due to symmetry. You can simply imagine that there shouldn't be any y-axis component for that point, because in another way, V is only a function of x. So if you take the derivative with respect to y, which should be 0, and this is actually EY. But actually, due to symmetry, you can already know that EY should be 0. Okay, so next one is a plastic wad has blended into a circle of radius capital R. It has a charge Q1 uniformly distributed along 1/4 of its circumference, and charge Q2 equals negative 6 Q1 uniformly distributed along the rest of the circumference. So with V equals 0 at infinity, what is the electric potential at the center of C of the circle? So this looks quite complicated, but actually this is really simple. So it is nothing but VC equals K times, for the green part, it looks like you need to do some integration, but actually they are distributed uniformly at least. But actually, whether it is uniform is not really important, because it is a circle, so that the distance between Z to this point and to this point or to that point are all the same, which means that it's just like you're integrating a constant, so that it turns out to be Q1 over R for the green part. And then for the orange part, it is nothing but Q2 over R. So it will be very easy, and which means that it will be like a K over R, Q1 plus Q2. So it is 8.99 times 10 to the 9th power. R is 8.2 centimeters, 0.082. And then Q1 is 1.2 times 10 to minus 12. And then plus, or maybe minus 6 times, because this is minus 6 Q1, minus 6 times 1.2 times 10 to minus 12. So it turns out to be minus 2.3 volt, minus 2.3 volt. So this is the first question, and then for part B. For part B, so what is the electric potential at point P on the central axis of the circle at distance this way? So actually the same structure, but rather than calculating the V as C, we calculate the the V at point P. So actually it is quite similar. The only difference is that we need to calculate this, maybe we can call it small r. Maybe we can call it small r. Small r is a square root of d squared plus capital R squared. So it will be 8.2 square plus 6.71 square. Take the square root, which is 10.6 centimeter. 10.6 centimeter. So in this case, VP is similar. So it is K times Q1 over small r plus Q2 over small r. So only changing the capital R to small r. So it is K, 8.99 times 10 to the 9th power over 10.6 centimeter, which is 0.106. And then Q1, 1 minus 6 times 10 times 1.2 times 10 to minus 12. So it is minus 1.78 volts. Okay, let's finish this one quickly. So we have a plastic disc, R equals 64 centimeter, and then D is 25.9 centimeter, and then using the this expression, without the 1/4, which is original derived, but now it only has a quarter of disc. We only have a quarter of disc, so that the potential at point P would be this expression, as long as we only have 1/4 of the disc. So V is like this, and it's asked you to find the V actually. So you only substitute the number 8. So 4 times 2 is 8. Epsilon naught is 8.85 times 10 to minus 12, and then sigma is this one, 7.73 times 10 to minus 15, and then Z here is capital D. This is capital D. So we have 0.259 quantity square plus R is 64 centimeters, 0.64 quantity square, take the square root, and then minus 0.259. So the answer will be 4.71 times 10 to minus 5 volts. So, and that's the end of this chapter.